Welcome. My name is Kartik Bali and my topic for presentation is convex hull problem. Before moving on to the actual problem of convex hull, let's take an overview of what is convex and concave. First, let's see what is convex. We call a shape convex if for any 2 points that are inside the shape, the line between these 2 points is also inside the shape. Let us consider this example. As we see, the points x and y are inside the shape and the line between x and y is also inside the shape itself. So we call this shape as a convex. Now let's see what is concave. If you see at a concave case, you see that it is easy to find 2 points inside the shape where the line has to leave and then enter the shape again. Here the 2 points x and y are inside the shape, but the line that joins these 2 points has to leave the shape and then re-enter the shape to meet the other point. Hence we can term this shape as concave. As we have figured out what is convex and concave in the previous slide, now let's move on to explore what is convex hull actually. Here, given a set of n input points, we can now define what we are going to call a convex hull. Formally, we can define a convex hull as convex hull is the smallest convex set containing all input points, and informally, we can define convex hull as if your points would be nails sticking in some piece of wood, the convex hull would be a rubber band wrapped around the outside nails. Uh, Here, this figure could be used as an example of a convex hull for the formal definition. Here we are given a set of input points, and the convex hull is the smallest convex polygon containing all the given points. And this would be an example of the informal definition where we are given a piece of wood on which we have placed some nails, and the convex hull would be the rubber band wrapped around the outside nails. Convex hull problem can be solved in two ways. First is gram scan algorithm and second is divide and conquer method. There are various applications of convex hull. The applications of convex hull could be first classification. Provided a set of data points, we can split them into separate classes by determining the convex hull of each class. Second, for collision avoidance, avoid collisions with other objects by defining the convex hull of the other objects. And in image processing and recognition, the demands of image processing are robustness, high recognition rate, and flexibility in capturing the shape of the object in an image. This is exactly where the role of the convex hull comes to play. For an example, we can consider here the original image is given of the horse. The convex hull could be this polygon which we see on the screen. Quick hull. Quick hull is a method of computing the convex hull of a finite set of points in n-dimensional space. It uses a divide and conquer approach to that of quicksort, for which its name derives. Quick hull algorithm. Under average circumstances, the algorithm works quite well, but processing usually becomes slow in case of high symmetry or points lying on the circumference of the circle. The algorithm can be broken down to the following steps. First, find the points with minimum and maximum x coordinate, as they will always be a part of convex hull. If many points with same minimum or maximum x exist, use ones with minimum or maximum y correspondingly. Second, use the line formed by these 2 points to divide the set in two subsets of points which will be processed recursively. Third, determine the point on one side of the line with the minimum distance from the line. This point forms a triangle with those of the line. Fourth, the point lying inside of that triangle cannot be part of convex hull and can therefore be ignored in the next steps. Fifth, repeat the previous two steps on the two lines formed by the triangle, not the initial line. And sixth, keep on doing so until no more points are left. The recursion has to come to an end and the points selected constitute the convex hull. Now let's see an example of a convex hull algorithm. Here we are given a set of points and the initial hull would look like this. Now we apply quick hull algorithm to the initial hull. The first step would be we find points with minimum x and x coordinate, minimum and maximum x coordinate, as they will always be a part of the convex hull. This is the minimum x coordinate and this is the maximum x coordinate. As there is no same x coordinate, we ignore the further instruction in the step 1. We join the minimum and maximum x coordinate with a line. As this line in the step 2, as this line divides the initial hull into two subsets, the top part is convex hull left and the bottom part is termed as the convex hull right. In the step 3, let's now compute the top part. Let's now compute the top part first, and we consider maximum y coordinate and form a triangle to the initial line with minimum and maximum x coordinate. This step would be like this. And then in step 4 we ignore all the inside points of the triangle. These points are ignored as they are not used to form the convex hull. Then in step 5, now we repeat the previous two steps, that is step number 3 and step number 4, on these two lines formed by the triangle. We work on this line and we ignore this line as this is the initial line. We keep on doing the step 5 until we come across this step. We keep on doing this until no more points are left and the recursion comes to an end and the points constitute the convex hull. Then we remove the intermediate steps lines and the convex hull would look like this. This is the final convex hull. This is an animation. This animation depicts the quick hull algorithm. First, then bottom sub part, that is right sub part, and then convex hull left is solved, and we get the convex hull, final convex hull. Now let's see the recurrence relation of convex hull. The divide and conquer convex hull algorithm has 3 steps. Split points into left and right halves. It takes O of n time. Recursively find the convex hull of each half. It takes 2t n by 2 time. And then we finally merge the two hulls into a single one by adding tangents, which takes O of n time. So in total we have t of n recurrence relation as t of n is equal to O of n plus 2t n by 2 plus O of n, which can be summarized and written as 2t n by 2 plus O of n. Now let's see the time complexity. Quick hull is the method of computing the convex hull of finite set of points in the plane. It uses a divide and conquer approach similar to that of quicksort, for which its name derives. Its average case complexity is considered to be O of n log n, whereas the worst case is it takes O of n square. In short, if we summarize what is the time complexity of quick hull, the average and best case time complexity for quick hull algorithm is O of n log n. For worst case, it takes O of n square, and the space complexity could be O of n. Thank you.